So welcome everybody to the third season of the Isogeny Club, episode 4. And today we have Luciano Maino. He's a PhD student in Bristol, and he's wearing a fantastic T-shirt as well. And today he's talking to us about computing chains of two isogenies and how this will improve FESTA.
Okay, can you all see my screen if I move the slide? Okay, cool.
Works perfectly.
Perfect. So first of all, thanks to Karen and Jonathan for giving me this opportunity. And yeah, today I'm gonna talk about, wait, let me move something on my screen. I have this bar, which is like super annoying. Okay, fix it. Almost, now fix it. So today I'm gonna talk about this, I mean, about like two main projects I did. Like I will combine a way to compute like two isogenies like in a faster way and pretty speed up to FESTA. So mainly I will follow two references. The first one is the paper from FESTA, and this is joint work with Andrea Basso and Giacomo Pope. And the other paper I will follow is an algorithm approach to isogenies in the theta model and applications to isogeny-based cryptography. This is joint work with Pierrick Dartois, Giacomo Pope, and Damien Robert. Okay, someone is writing on this. Okay. So let me give you like an overview of what I will talk about. First, I will, introduce FESTA, how FESTA works. Then I will discuss about its security, and I will try to convince you and also convince myself that the protocol is robust enough. And then I will argue that it's robust enough so we can actually focus on speeding up other building blocks. And one of the main building blocks of FESTA is the computation of a chain of two isogenies between elliptic curves, products of elliptic curves. And we do that using like the theta model. So I will talk about the theta model and how to compute isogenies in the theta model, and then I will draw some conclusions. So let me start with FESTA. So FESTA is a protocol based on the SIDH attacks, and everybody knows about SIDH. SIDH was previously introduced by DeFeo, Zhao, and Plut in 2011, and then in 2017, Petit described some attacks on some parameter sets of SIDH. This attack did not affect the security of SIDH at the time, but rather certain parameter sets. So using this attack, then DeFeo, Desaguliers, Fuozza, Kutash, Leroux, Petit, Silva, and Vesolowski designed like a trapdoor mechanism. And using like a standard transformation, this trapdoor mechanism, they design a PKE, which is a public key encryption mechanism, which is in CCA secure. They call this protocol theta, which stands for super singular encryption from torsion attacks. Then, I'm pretty sure that any of you, knows about new attacks on SIDH that appear in 2022. So using these attacks, we design a trapdoor mechanism, and applying the same transformation as in theta, we design a public key encryption mechanism, which is in CCA secure. And okay, I didn't say it. FESTA stands for fast encryption from super singular torsion attacks. So I would just let me just remind you let me give you like one sentence about the SIDH attacks. So we have a secret isogeny phi, and this isogeny has degree D, and we have a torsion basis PQ. And when we have that the image of PQ under this secret isogeny, and we have that N is large enough, then it's possible to recover the isogeny phi. This is what we are going to use to design a trapdoor mechanism. Okay, so rather than explaining you how to obtain like the public key encryption, I will tell you how we design like a trapdoor function, and then we'll skate over what's the transformation to apply to this trapdoor function in order to obtain the public key encryption mechanism. So a trapdoor function is a triple of algorithms. We have keygen, f, and f minus 1. On keygen, in keygen, we have on input lambda, keygen outputs like a pair of keys, like a secret key and a public key. And then we can evaluate f at any input x if we have access to the public key pk, and let's call the output of this f y. And then we can evaluate f minus 1 at the output of f y using the secret key, and this will return x. So of course we need some properties. So the first property that we need for our trapdoor function is that should be correct, which means that for all public keys and inputs x, we have that f minus 1 sk of f pk x is equal to x. And then the other property that we need is that this trapdoor function should be one way, which means that given a public key and an output y, finding an x such that f pk x is equal to y, this is actually a hard problem. So, okay, this is kind of a notation that I will use in the next slide, and I'm gonna explain how to construct a trapdoor function and how we do that in FESTA. So in FESTA, we have some parameters, some public information, some public setup, which is given by an elliptic curve E0. And on this elliptic curve, we fix a basis, PBQB. I will tell you how we pick this basis and what we use the specifics for this basis in the next slides, especially when I will argue security. And then, so this is kind of part of the public setup. For the secret key, we have an integer alpha and the secret isogeny phi a. The secret isogeny phi a originates from E0 and maps onto EA. And then we use this scalar alpha to mask some torsion. So basically we evaluate phi a at PB and QB, and then we mask phi a PB by alpha and phi a QB by the inverse of alpha. And we call the scale torsion RA and SA. So then the secret key will be given by the secret scalar alpha and the isogeny phi a, whereas the public key will be given by the elliptic curve EA and the scale torsion A. Then we need to evaluate our trapdoor function. So the input will consist in two isogenies, phi 1 and phi 2, and another scalar, beta. So the isogeny phi 1 originates from E0, and we map PB and QB under the isogeny phi 1, and we mask phi 1 PB by beta and phi 1 QB by beta, the inverse of beta minus 1. And we call this, we know these points with R1, S1. We do the same process on phi 2, which is the second isogeny in the input of our trapdoor function. And we evaluate phi 2 at RA and SA, and we mask phi 2 RA by beta, the same beta as on the left side here. And we do the same for SA, and we call this mask torsion R2 S2. So basically, the output of our trapdoor function will be given by the curve E1, then mask torsion R1 S1, and the curve E2 and the mask torsion R2 S2. Now we need to understand how to invert the function, a trapdoor function. To do so, we consider another isogeny. This isogeny is the isogeny psi. Psi is an isogeny connecting E1 and E2. So psi is given by the composition of the dual of phi 1 composed with phi a and again with phi 2. This psi verifies some properties. The property we are interested in is the following one. We know that if we evaluate psi at R1 and S1, we have the following, I mean, we have the following equation. R1 psi S1 is equal to R2 scaled by the inverse of alpha, and S2 scaled by alpha, and everything scaled by the degree of phi1, which means that if you have access to your secret key, and especially to the scalar alpha, you can actually evaluate the isogeny psi at a certain torsion, and using the SIDH attacks, you can actually recover the isogeny psi. Then from the isogeny psi, you can recover phi1 and phi2, and from phi1 or phi2, you can recover beta, and everything works. So you are able to invert the Trapdoor function. So now let me be a little bit more specific. I'm gonna go a little bit on the mathsy side of the talk. So we need the tool that we need, the theorem that we are gonna use to invert our Trapdoor function is Canis criterion. So let me state it, we need like two isogenies, phi n1 and phi n2, both of them originating from E0. And we know that and we must have that the degrees of these two isogenies are actually coprime. So the degree of phi n1 will be n1, and the degree of phi n2 will be n2. And then we look at this subgroup in E1 cross E2. Let's look at this subgroup K. This is a group of rank 2. And the first generator is given by this pair of points on elliptic curves. So the first coordinate of this pair is given by phi n1 p scaled by n2, and the second component phi n2 p scaled by n1. And then for the second generator of this subgroup here, we have the same thing, but rather than using p, we use q. And we know that, and what are p and q? P and q are two generators of the n1 plus n2 torsion of E0. So this is kind of the initial data that we need before stating the theorem. And once we have this, then we can we know that the isogeny having kernel K is an n1 plus n2, n1 plus n2 polarized isogeny phi. At the moment, like, ignore the word polarized. I will come back to this, and everything will become explicit when I move to the second part of the talk, when I will give you more details about the maths behind this theorem. The only thing that we should remember right now, and we are going to use right now, is that this matrix here has like a nice matrix. This isogeny here has a nice matrix form, and especially the first row of this matrix is given by the dual of phi n1 and the minus the dual of phi n2, and then the second row will be given by gen2 and the dual of gen1. The isogenies gen1 and gen2 are basically the isogenies completing the SIDH square, and basically that's the relation that they verify. Another remark is that the computation of this isogeny is part of the inversion for our trapdoor mechanism, which means that we would like that the computation of this isogeny should be as efficient as possible, as fast as possible. To do so, like in complete analogy, what you do with the one-dimensional isogeny, you want to have that the degree of your one-dimensional isogeny should be smooth enough. And in the case of dimension 2, you want the same, which means that you want n1 plus n2 to be smooth, and in particular to have since computing isogenies in dimension 2 can be a little bit demanding, you want that n1 plus n2 in practice will be a power of 2. And that's what we are going to use in FESTA. So now let me explain how to do like the concrete inversion algorithm for the trapdoor function. So this is the graph, the diagram we do before. The only thing that I modified here is that rather than considering phi A as a unique isogeny, I've split phi A into different isogenies, phi A1 and phi A2. Why did I do that? Because then I can realign, I can split some isogenies like into parts and realign with the previous criterion, with Canis criterion. So I can have like an explicit matrix form for our two-dimensional isogeny. Well, so how do we do so? So let's call the degree of phi AI dAI and the degree of phi I dI. Then we need to find two integers, m1 and m2. For these integers, it doesn't matter if they are smooth or not. They can be anything. I need to find these two integers, m1 and m2, such that m1 squared times dA1 times d1 plus m2 squared dA2 d2 is equal to a power of 2. So this quantity here, this quantity here will be will play the role of n1, and the second quantity here will play the role of n2. And the other condition that we have on these quantities is that they are coprime. And then we look at these isogenies. I call them phi 1 and phi n2 because I'm using the same notation as before. So the isogeny phi 1 is given by the dual of phi A1 composed with phi 1, and then we have a scalar multiplication. The scalar multiplication is given by m1. So the degree of phi n1 will be exactly the first quantity here, and we do similar reasoning for phi n2. We go from E tilde A, we go all the way down to E2, and we compose it with scalar multiplication. The other conditions that we need for these isogenies, of course, I mean, all the degrees of these isogenies must be smooth enough so we can compute them efficiently. And the other thing that we need is that di should be larger than 2 to the 2 lambda, and dA1 times dA2 should be larger than 2 to the 2 lambda. I actually explain later on why we need this this condition to ensure security. So then now it's just a matter of putting substituting these quantities in the theorem before, the criterion that I stated before, and then we obtain this kernel here. So yeah, if you do like the maths, you will obtain exactly this kernel. The only thing that I want to point out here is that this kernel actually, this kernel does depend on alpha, and this alpha is a secret scalar. So in order to construct this isogeny, you need access to the secret alpha. Once you have this kernel, you can compute this 2 to the b isogeny. And the cool thing about this isogeny is that on the first row, you will reveal the dual of phi 1 and phi 2. So let's analyze the first component. In the first component, you have the dual of phi 1 composed with phi A1 composed with the scalar multiplication. And so M1 is public, is a parameter, so everybody knows that. Then phi A1 is part of your secret key, and that's the reason why I split phi A into parts. So if you know how to evaluate phi A1, then you're done, because I mean you can recover phi 1 dual, which means that you can recover phi 1. You do the same trick on phi 2, and then from phi 1 you can recover the scalar beta, and you're done. So this is the rough outline. So this is how the protocol works theoretically. And now let's discuss a little bit the security of this protocol. So first of all, a natural attack you can do, and I want to mention here that this reasoning was pointed out to us by us, I mean like Andrea, to us means like me, Andrea, and Jack by Boris. So let's do like the first approach that one can try to attack FESTA is to guess some torsion. So we have an isogeny phi, and we have some masked torsion. The masked torsion is masked by alpha. So what we do, we let n be an integer such that 2 to the n is greater or equal than 2 square root of degree of 5. Then the idea is, rather than guessing alpha, we just guess alpha modulo 2 to the n, and then we apply Robert's attack in dimension 4. So doing so, it means that rather than looking at the entire R and S, we look at the, we scale R and S by 2 to the n minus b, and we obtain R prime and S prime. And then it's just a matter of finding a beta, an odd beta, such that this equality holds. So that means that we know how to evaluate phi at the 2 to the n torsion, and then we can run the attack. So assuming that the cost of running a Robert's attack is negligible, that you need that the degree of phi should be larger than 2 to the 2 lambda, and that's the reason why we have that condition in the previous slides. Actually, I think that maybe if one takes into account that computing like 4-dimensional isogenies can be has a certain cost, you can actually argue that you need maybe shorter isogenies phi, but I think that the field is not mature enough to make such assumptions and to try to have like shorter parameters. So for the moment, it's better to be conservative. So this is one approach. And using this approach, we found some parameter sets, and these are concrete parameter sets for FESTA, and this ensures 128 bits of security. You don't need to remember all these numbers. The only thing that I want to point out is that this B is equal to 632. And this is something that we're going to use later on. And it's actually, this B denotes the length of the 2-2 chain we are going to compute. And the other thing that I want to point out that the degrees of the isogenies phi1, phi2 are smooth. And these are smooth enough, so the computation of this one-dimensional isogenies is not too complicated, it's not too burdening for the evaluation of the disruptor function. And another approach that one can try to attack FESTA is this attack from Kastrick and Varkarauten that appear in, that will be published in AsiaCrypt 2023. This is a generalization of the lollipop attack. So we are exactly in the same scenario as before. So we have this isogeny phi, and we have some mask torsion. In the lollipop attack, we basically look at an endomorphism on E, on this curve E. The endomorphism is given by the composition of phi dual composed with a certain endomorphism omega, and then we compose it with phi again. So for certain parameter sets, and if the torsion is not masked, this could work, but it turns out that it might be not enough to attack these type of problems in the parameter sets in FESTA. So for this reason, Kastrick and Varkarauten generalized the attack, and rather than using just the dual of the isogeny, they look at the Frobenius conjugate of the isogeny. So what they do is that they look at this new isogeny psi. This isogeny psi is given by the dual of phi composed with an endomorphism omega on E0 composed with the Frobenius conjugate of phi. And then for this attack to work, there is another assumption. The assumption is that the basis here that the points that we are evaluating here under phi must be eigenvectors for the endomorphism omega composed with pi, where pi denotes the, as usual, the Frobenius endomorphism. And if this is the case, then we know how to evaluate the isogeny psi at R and S. And this the evaluation of psi at R and S is given by this quantity here. So the condition in the second bullet point can be a little bit restrictive, but there are certain cases where it might happen. And now let's look at the case of FESTA. So first of all, in this case, we need pi to be an endomorphism. I mean, that's not, there are other cases when the attack can apply. For instance, if the starting curve is 0 is close enough to an FP rational curve. But for the sake of hand, I mean, I will just describe the easy case and we'll just briefly sketch the attack. So for the case of FESTA, for the proof of concept implementation that we gave, the starting curve is FP rational, but there is no need for this curve to be rational. I mean, the protocol works even if you pick a curve which is not FP rational. We are not using the knowledge of the endomorphism ring. So the curve must be FP, in this case, the curve is FP rational. And then we need like the 2 to the b torsional basis, which is actually the points P, B, and QB given as part of the public input, the public setup for FESTA. This torsional basis must be a basis of eigenvectors for certain endomorphisms. But in our case, we generated the 2 torsional bases using like a modification of the alligator map. And this is kind of that was an improvement, a speed up that was given by Zanon, Simplicio, Pereira, Doliscani, and Barreto in a paper from 2017, where they applied this kind of modified version of the alligator map to generate the 2 to the b torsional basis in SIDH. And so since the alligator map acts as a way to hash points on elliptic curves, we can assume that the generation of this, the 2 to the b torsion basis generated via this method gives you back something a basis which has not enough information. I mean, like a basis which is not particular in any way. Let me clarify what I mean with this. So for the attack to work, we need like the second bullet point to apply. So there are actually 2 cases. In the first case, we need that P and Q, both of them are eigenvectors for a certain endomorphism. This endomorphism is given by omega composed with pi, and the number of bases PQ such that we have that PQ are eigenvectors for endomorphism omega composed with pi, and the degree of omega is 2 to the 2b over degree phi squared. I mean, this number, the ratio between this number and the number of all the possible 2 to the b torsional bases, actually the ratio is a big O of the minimum between 2 to the minus 4 lambda and 2 to the minus b. As before, b was, as I showed you before, b is like 632. So the probability of having such a basis verifying this condition here is extremely low. And there is actually another modification. I mean, like rather than looking at P and Q such that both of them are eigenvectors, they also look when just one between among P and Q is like an eigenvector for this endomorphism. And then they study the ratio between all the possible basis such that among P and is an eigenvector for this endomorphism, and degree of omega is smaller than 2 to the b over degree phi, and they compute this ratio over all the possible 2 to the b torsional bases. And again, this estimate this to be big O of 2 to the minus 4 lambda. So again, the probability of having such a basis is extremely low. Anyway, there are certain instances when this attack can apply, and it's actually possible to craft such a specific endomorphism omega. And this is the case when 2 to the b is larger, is greater, and actually similar to p times d cubed. But in this case, you're not looking at FESTA, because I mean, in this case, the 2 to the b torsion will be a huge extension field, and the protocol FESTA itself will not be practical. And so this attack does not apply to FESTA, but despite that, it's still like interesting, and it can give you new insights on how to generate, I mean, actually beyond like the cryptanalytic side of cryptography, maybe also for constructive applications. Okay, now I'm gonna move to the more mathsy side of the talk. And here we talk about how to compute explicitly these 2-dimensional isogenies and how to do so in the theta model. Now I'm gonna give you like a little bit of intuition for why do we need to consider polarizations. So when I stated the Canis criterion, I said that we obtain a polarized isogeny, but what's a polarized isogeny? So let's look at something that we all are familiar with, which is like the case of an elliptic curve. Whenever we have an elliptic curve, we implicitly have some additional structure. So by the Riemann-Roch theorem, we have an isomorphism, between the curve E and its dual, peak zero of E. The dual, I mean, it's not relevant to know what's the dual of an elliptic curve. And when I say peak zero of E of the Picard zero of E, I'm referring to the group generated by the group of all equivalence classes of divisor of degree zero over the principal divisors. So what's fundamental here is that we have an isomorphism between E and its dual. In practice, this isomorphism is described by a line bundle, and this line bundle is associated with a specific divisor, and this divisor is exactly the divisor given by the point at infinity. And why did I do all of this? Well, the point is that we have just described a principal polarization, and that's the reason why the correct generalization to higher dimension of curves, so if we go up in dimension, we need principally polarized abelian varieties. So let me try to describe what a principally polarized abelian variety. So we take like A in abelian variety. Again, the moment I'm just giving like some kind of abstract maths, but then I will give you explicit equations. So I will try to specialize what I'm saying more and more. I'm just gonna narrow it down more. So we take an abelian variety. A polarization is just an isogeny psi from A to its dual. And this isogeny psi comes from a line bundle, as in the case of elliptic curves. And then we say that the polarization is principal when the polarization is also an isomorphism, like in the case of elliptic curves. Why do we care about the principally polarized abelian varieties? Is that if we have like two principally polarized abelian varieties, then we are just able to compute isogenies that are compatible with. What does it mean? So we say that an isogeny F between A and B, connecting A and B, is an n-isogeny if the polarization of A composed with the scalar multiplication of n is equal to the dual of F composed with the polarization on B composed with F. And that's the meaning of an n-isogeny respecting the polarizations as well. This condition is automatically verified for elliptic curves, but when we go up in dimension, we need to be sure that we work with principal polarized abelian varieties. Now, for the case at hand, let's just focus in dimension 2. And in dimension 2, we just have two types of principal polarized abelian surfaces. Products of elliptic curves, which are extremely interesting for cryptographic reasons, and Jacobians of hyperelliptic genus 2 curves. So for the moment, I'm not going to give you like a description of hyperelliptic genus 2 curves, because then to compute isogenies, we are going to look at the theta model. And the theta model is kind of oblivious to the principal polarized abelian surface we are describing, which means that it doesn't matter which abelian surface we are describing. We just have some coordinates that are kind of uniform. This is kind of true. I mean, there are some edge cases, but I will tell you more later on. And just a little bit of notation. Okay, there is a chat, a message in the chat. Are A and B? Yes, thanks. Thanks, yes, sorry. So I will just read it again, the message, the question. Are A and B swapped in the second bullet? Yes. I did it, sorry. Thanks anyway. So we know we denote like the n isogenies in dimension 2 by nn, because I mean, since in cryptography, I mean, at least we use both one-dimensional isogeny and two-dimensional isogenies. This is kind of a way to, you know, distinguish between these two types of isogenies. Okay, so now let's move on to actually the goal of the second part of the talk. We want to compute chains of two isogenies between elliptic products. So our goal is to compute a 2 to the b isogeny F, originating from an elliptic product E1 cross E2, mapping onto E1 prime cross E2 prime. As in the one-dimensional case, of course, we can compute F as a chain of two isogenies. This chain is given by F1 composed with F2 till Fn. In this case, that's Fb. Again, that's a typo. So, is there a question? So, since I said that there are like two types of principal polarized abelian surfaces, there are like four types then of two isogenies. So the first type is like are isogenies between elliptic products, but these isogenies are actually trivial because I mean their kernel is given by the product of one-dimensional kernels. So we are not gonna deal with this case because I mean that's basically the same case as for one-dimensional isogenies. Rather, we are gonna look at the three cases. So in the first step of this isogeny chain is given by the so-called gluing isogeny. So we look at an isogeny F1 originating from an elliptic product E1 cross E2 and mapping on the Jacobian of a hyperelliptic genus 2 curve. There are formulae to compute these isogenies, and for instance, a reference for this can be found in the paper by Owen, Leprost, and Poonen from 2000. So this is kind of the first step of the isogeny chain. Then we have another particular step is the last step, which is the splitting isogeny, where you map from the Jacobian of a genus to hyperelliptic curve onto an elliptic product. Again, there are formulae to compute this type of isogenies, and these are described in the PhD thesis of Ben Smith. And then all the intermediate cases, actually there might be that you go through another elliptic product, but again, then you split again this chain of isogenies and you look just a chain where the intermediate steps are isogenies between Jacobians. And the isogenies between Jacobians are really like dominating case. And there are ways to compute these isogenies. A formula to compute this isogeny is given by the so-called Richelot isogenies. These formulae are described. A reference for this formulae can be found in the PhD thesis of Ben Smith. And so these formulae actually are extremely elegant from a mathematical perspective, but from a computational perspective, whenever you want to implement them, they can be a little bit challenging and they can be slow because you will work with univariate polynomials over the base field, which means that you have to deal with this. You have to work with polynomial operators. You have to multiply polynomials, and this can be a little bit demanding and expensive. For this reason, rather than explaining this formulae and looking at how to speed up this formulae, we decided to go for like a different approach. This different approach is given by the theta model. So let me explain you let me give you some rough insights about what's a theta structure and how we can work with it. So again, we start from A. Let A be a principal polarized abelian surface. And for instance, what about dimension greater than 2? Does the Jacobians of curves if genus G polar does the Jacobians of curves if genus, can you Can you try to explain it better? There is a question in the chat.
I'm talking about the curve of genius 2. Is it polarized?
Yes, Jacobian, yes. Yes, Jacobian is always principally polarized, if that's the question. Yes, okay. Was it the question?
Okay, thanks.
Okay, perfect. So yeah, let's discuss a little bit the theta structures. So we have like our principal polarized abelian surface. And in this case, we have a product. Let's just to have like a concrete example in mind, let's just work with a product of two elliptic curves. And then let's fix a symplectic fourth torsion basis on this principal polarized abelian surface. What does it mean? This is kind of useful notation that we are going to use throughout the talk, and it will accompany us till the end of the talk. So the symplectic fourth torsion basis is denoted by S1 prime, S2 prime, and then T1 prime, T2 prime. What's the meaning of being symplectic? It means that the pairing between S1 prime and T1 prime is equal to the pairing S2 prime, T2 prime. And this is basically a primitive fourth root of the unity. And then all the other pairings between other points, all the other possible pairs of points have pairing equal to 1. So once we have this symplectic fourth torsion basis, this symplectic fourth torsion basis defines 4 functions called like theta functions, and these theta functions are useful to define and useful to describe the Kummer surface of this abelian surface. So in this case, we order these functions using the following indices, like theta 0, 0, theta 1, 0, theta 0, 1, theta 1, 1. This ordering matters, especially when we need for the formulae I'm gonna describe later on. In this way, using these functions here, theta functions, we have a way to describe the Kummer surface inside the projective space. And a good property about this theta function is that we can describe the Kummer surface just by looking at the projective point, just by evaluating the theta functions at the identity of the principal of the identity on A. And looking at this point, this projective point, we can actually reconstruct the abelian surface itself. So now let me give you like a precise concrete example. So this example actually builds on top of the case of the one-dimensional case. Let's look at the elliptic products. At the end of the day, that's the abelian surface that matters the most to us, because we need to endow this abelian surface with a theta structure to start our algorithm. So in season 3, episode 3, which is like the previous talk, Sarkis gave conversion formulae between the Montgomery curves and its theta squared model. So then picking any square root of the square theta null coordinates, we obtain a theta structure on an elliptic curve. In practice, that means that we have an elliptic curve E, and then from this elliptic curve, we define a theta null point, and we call this theta null point, we denote the coordinates of this theta null point by A and B. Then using this, as I said before, the evaluation of the theta function, the identity, which is called a theta null point, is enough to describe the entire Kummer surface. And now I'm going to give you explicit equations. So if we have a point P in E, on E, where like in Montgomery coordinates, x, z, then we can move it to theta coordinates just by in this way. So theta 0 of P will be equal to A times x minus z, and then theta 1 of P will be equal to B times x plus z. So in this way, we have conversion formulae. And when we look at the elliptic product E1 cross E2, then we can endow this elliptic product with the product theta structure. And this product theta structure is really handy. And I will give you like explicit equations to work with theta structure. So each curve can be, starting from each curve, we can convert between the Montgomery model and the theta model. And then if we have like a pair of points on this elliptic product, we can actually convert to the theta model of the elliptic product in this way. So the first component will be given as the product of theta 0 E1 P1, theta 0 E2 P2, and then all the other components follow the ordering that I've described before. So for instance, here we have 1, 0, and then here we have 0, 1, and then in the end we have 1, 1. This is just to say that we can actually, this is practical, and we have a way to endow elliptic products with theta structures. So another ingredient that we need, I'm just going to introduce some operators. And this is basically everything that we are going to need to describe isogenies in dimension 2. So we first define the Hadamard operator. You don't need to remember what's this matrix, but what you need to remember is that the Hadamard operator is just basically you take a vector of 4 elements and then you multiply this vector by a certain matrix. It's just basically matrix multiplication. And once you have some coordinates of a point P, and you apply the Hadamard transform on these coordinates, you obtain the so-called dual coordinates of P. And we denote these dual coordinates by a tilde on top of the thetas. Another properties of this Hadamard transform is that if you apply 2 times the Hadamard transform, then you have that in the projective space, you obtain the same point, which basically means that dual of the dual is the point itself. And that is meaningful, makes sense. So this is the first operator we need to remember, which is basically just this matrix multiplication. Then we need to remember another operator, the squaring operator, which basically you take a vector with 4 elements and then you square each element. So it's just you are just squaring x, squaring y, z, and w. And then the last operator is the star operator, which basically describes a component-wise multiplication between 2 vectors. So now we just need these 3 operators, these 3 ingredients, and then we are able to describe the entire isogeny formula. The isogeny formula comes from the duplication formula. So now let's recall this notation. So as before, as I said, like in the previous slide, we have a theta structure coming from the symplectic decomposition, right? And here we look at this isogeny F originating from A and mapping onto B. And the kernel of F is given by T1, T2, where the TIs are basically 2 times Ti prime. That's the reason why we have prime here. And then looking at this isogeny, we have the following relation that we are going to use to obtain other formulae. So if we take P and Q to point on A, we have that the theta coordinates of P plus Q star the theta coordinates of P minus Q, that's equal to the Hadamard transform applied to the dual theta coordinates of Fp star the dual theta coordinates of Fq. So once we have, using this relation here, we can obtain additional formulae. I'm just going to give you like a rough intuition on how to do so. So for the doubling, you basically compute an isogeny and then compute the dual of that isogeny, and that's basically a scalar multiplication. That's how you obtain the doubling. And similar reasoning, you can obtain differential addition. And the cool thing about this is that we can actually give like precise operation counting. And these formulae have been described in a paper by Gavri from 2005. And so from this duplication formula, we can first obtain additional formulae. But more than that, and most importantly, we can obtain isogeny formulae as I will describe later now in the next slide. So now let's assume that the goal is to compute the isogeny F originating from A and mapping onto B. And the kernel of this isogeny is specifically T1 and T2. Let's make another assumption that we have another isotropic group, T1 double dash, T2 double dash, and isotropic means that the pairing between T1 double dash and T2 double dash is equal to 1. And we have that T1 prime is equal to 2 times T1 double dash, which means that the Ti double dash lay above Ti prime. So if we have this condition, and this condition is actually not really restrictive, especially in the case when you are chaining isogenies, because I mean, this information comes from part of the kernel above the comes from part of the kernel you are using to compute the specific step. So for the moment, just assume that we have this additional information. And then let's define with alpha, beta, gamma, and delta the dual theta null point on B, which is like the image surface. And then what we have here, I just need you to believe me. I mean, like we did the maths, and this relation holds. So if we apply this squaring operator composed with the Hadamard operator onto the theta coordinates of T1 double dash, you obtain X alpha, X beta, Y gamma, Y delta. And if you do the same, you apply the squaring operator and the Hadamard operator on the theta coordinates of T2 double dash, you have X alpha, W beta, X gamma, W delta. And you don't know, I mean, the goal is to recover alpha, beta, gamma, delta, but the quantities X, Y, Z, W are not known to you, but that's not relevant, because I mean, what we're going to do right now is that we will recover the dual theta null point, alpha, beta, gamma, delta. So for instance, so this is the point we are going to recover. Since we are working projectively, let's divide everything by alpha. So the first coordinate will be 1, and then we have B over alpha, gamma over alpha, and delta over alpha. So for instance, the coordinate B over alpha can be computed as X beta over X alpha, and you have B over alpha, and the same you can do for gamma over alpha. You just divide X gamma by X alpha, and then you do the same for delta. And for delta, you need to combine other relations. In this way, you have access to the dual theta null point, and then by just applying the Hadamard, you obtain the theta null point on B, and that basically you have obtained a complete description of B, because I mean you have a theta null point on B. So this is the algorithm to compute the codomain of this isogeny, but actually we can use similar reasoning to evaluate this isogeny F at any point P. So what we do is that if we have the theta coordinates of P, then we apply the squaring operator, we apply the Hadamard operator, and then we multiply it. We just compute like this quantity star alpha minus 1, beta minus 1, gamma minus 1, gamma to the minus 1, and delta to the minus 1. And this way we obtain the dual theta coordinates of FP, and then again we apply the Hadamard transform and we obtain the theta coordinates of FP. And this is basically the algorithm to compute the isogenies. So as I said before, you just need like the operators, the squaring, the Hadamard, and the star operator. And now I'm just gonna talk briefly about the dust under the carpet. No, actually not. First, I will tell you like the precise operation counting, and then I will tell you some details I've skated over. So before I said that the theta model is kind of oblivious to the type of abelian surface you're describing. This is almost true, but some extra care must be taken when you compute the gluing isogeny, which is the isogenies between originating from an elliptic product and mapping onto the Jacobian of an elliptic curve. And this case is handled in a different way. So for this reason, you have a different operation counting. But for the generic case, then you have that doubling, as I said before, amounts to 8 squares and 6 multiplications. Whereas for the codomain, if you have access to additional information, that's the optimized case we pointed out here. If you have access to additional information, which is basically what can come from, like, if you do some arithmetic on the on certain abelian surface before computing the isogeny, then you can lower the generic cost of the codomain, which is given by 8 squares, 29 multiplication plus 1 inversion. You can lower this cost to 8 squares, 9 multiplications, and 1 inversion. And then the evaluation of a generic 2-2 isogeny requires 4 squares plus 3 multiplications. For the gluing, it's a little bit different, because I mean, what in practice, what you may have is that one of the dual coordinates of the theta null point can be equal to 0, so you need to do an additional step. But I have not described this step, and you can find detail. I refer to the details in the paper to understand better what's going on. And now some details I've skated over. So the formula I've showed you assume that the kernel of F, the fourth torsion of the kernel of F, is actually aligns with T1 prime, T2 prime, but actually that might not be the case, and most of the cases it's not. So what you need to do is that for the first step, for the gluing isogeny, yes, you need to perform a change of basis. And this correction formula changes the symplectic basis giving you the theta structure. This correction formula requires 100 multiplication plus 8 squares plus 4 inversion. This is kind of a constant cost, so it's kind of a constant overhead, which means that no matter what's the length of your isogeny, this is a step that you have to perform anyway. And then another detail that I've not talked about is that at the end of the chain, we are left with an elliptic product in theta coordinates. So for like cryptographic reasons, we would like to work over the Montgomery model of these curves. So we need to switch from the Montgomery model for these curves, from the theta model of this elliptic product to the Montgomery model for the two curves. And there are like just 10 transformations giving you a specific structure for this product of Montgomery curves. So since there are just 10 of them, and there are very few of them, we hard-coded all the possible transformations for efficiency reasons, and applying this transformation just amounts to like a matrix multiplication. And this step is not expensive, and I've not discussed that. And now, okay, so now let's address a little bit the elephant in the room, and let's give some concrete timings. So these are some running times of computing the codomain and evaluating 2 to the n isogenies between elliptic products, and this is done over fp squared. So the times we're recording on an Intel Core i7 with a clock speed of 2.6 gigahertz, and the turbo boost was disabled, which means that we have a slowdown. I mean, if you use the turbo boost, then roughly all the timings will be halved. So we implemented the algorithms in Rust and SageMath. The implementation in Rust, I mean, the implementation between Rust and SageMath are actually not really comparable, because I mean, the implementation in Rust is designed to run in constant time with respect to the arithmetic on the base field, and also it's not dependent on on conditional branching from the secrets we are using. So this implementation is designed for like cryptographic purposes and is designed to run in constant time. And whereas the SageMath implementation is not designed to run in constant time. And so here, let me explain the 3 columns. So in this column, we describe the implementation that we use in FESTA, which employs Richelot isogenies for the isogenies between Jacobians of hyperelliptic genus 2 curves. And moving from this algorithm to the theta algorithm, we have a constant like 10-fold speed up every time. And then when we move from the implementation in SageMath to the implementation in Rust, we obtain, like, in this case at least, roughly a 40 times speed up. And as you can notice, going farther, the bigger the characteristic, the lower is the gain for like, the lower is the ratio between the gain that you obtain from the SageMath implementation Rust. That is because in SageMath you have some time is spent in between converting between different types, and that's kind of a constant overhead that doesn't matter the characteristic of the field. Whereas here, the characteristic of the field matters for the Rust implementation. And also for the evaluation, we can see that the Rust implementation, the theta implementation performs really well compared to the implementation using Richelot isogenies. And this is really promising, and this means that there might be a future, for two isogenies in isogeny-based cryptography, like for practical use of these isogenies. And now let me give you, I've talked about FESTA before, so now let's discuss some timings for FESTA when we apply this formulae. Here for like an honest comparison, we compare it with the same hardware that we used in the paper of FESTA, and this is basically Andrea's laptop. And the only thing that I want to point out is the encryption goes down from 10 seconds to 2.823 seconds. And this is like a 4-fold speed up. We don't obtain like more speed up than that, like not a 10-fold speed up, because right now the bottleneck for the decryption, actually not the bottleneck, the slowest part for the decryption is actually given by working with elliptic curves rather than working dimension 2, which means that if we want to improve FESTA more, we need to look at dimension 1 again rather than improving dimension 2. And this is kind of mind-blowing if you ask me. And okay, let's draw some conclusions. So these two isogeny formulae can speed up all the protocols currently relying on chains of two isogenies. So for instance, the protocol IsCube described by Tomoki in the second episode of this season. And the same applies for QFESTA. In particular, Jack designed this implementation in SageMath to be a drop-in replacement for like the implementation used in FESTA. So if your protocol uses an implementation in FESTA to compute like chains of two isogenies, you can just basically with minimal effort you can change those algorithms with these new ones and obtain and have like a nice speed up as well. And then other open questions that remain are like, what about LL isogenies? I mean, what about when L is odd? Can we use the theta model to have nice results? Can we optimize these computations? I mean, there are algorithms to compute that. And the other point is that, can we optimize like the computation of two isogenies, like two isogenies in dimension 4? And this will be extremely relevant and useful for SkiSign-HD. And that's all I wanted to say. So thanks for your attention.
Thanks a lot.
Thanks
Luciano,
for a great talk. Oh, sorry.
If you have any questions, feel free to either unmute yourself or to type them in the chat, whatever you prefer. Actually, I have one to start out with, because I was wondering at the results you had for evaluation. What does it actually mean? What are these timings? So this 161 millisecond, for example.
Give me a sec, okay. Well, I mean, you're evaluating an isogeny and two isogeny at a certain point. So you take a point and then you compute f of a point P, and then you compute f of P.
But then is you took the timing of one evaluation and you multiply it by doing it 126 times, or?
Yes, this should be like through the chain, because I mean the evaluation. No, sorry, that doesn't not mean that. So you compute the entire chain. I was wrong, sorry. I was confusing myself. So you take the entire chain of two isogenies, and then you obtain an isogeny F between elliptic products, and then you evaluate this isogeny F. That's what it means. So it's not just a 2-2 isogeny, but the entire chain of isogenies.
Check. So my question is, let's say I want to do a 2n2n isogeny F, and I want to evaluate it on 2 points. Do I need to well, I guess computing the codomain would take 2.85 milliseconds, and then is the 160 microseconds additionally, or do I could I do this separately after computing F?
Yes, yeah, you can do that separately after computing F, and that's what is done in FESTA.
Ah, well, okay, impressive.
Maybe I could also ask a question if you guys can hear me. So I just wondered if you did you compare like the timings for computing one of these 2 to the n, 2 to the n isogenies with just computing a 2 to the n isogeny in dimension 1?
Yes, we do have some timings in the paper, and yeah, I've not included them in the presentation, but yeah, you can look.
Okay, nice. It's still comparable.
Yeah.
Yeah. Thanks.
Thanks for the question.
And maybe a last question, or if people are typing in the chat, then you need to hurry up a bit. What is now actually the bottleneck? You said it's in the dimension 1 elliptic curve arithmetic, but what is slow there?
At the moment, what's are you referring to FESTA, right? Yeah, I assume so.
Yeah.
Well, you need to compute a D-log, and D-logs can be demanding. Yeah, that's basically, I guess, right now the main bottleneck. Let me think about that. Yeah, basically, D-logs.
Check. So a quantum computer would come in handy.
Do we have existing formulas in dimensions 4? In dimension 4, yes, we do. Thanks, Eric. Yes, indeed. My last point was actually not to implement this formulae in dimension 4. It's more like optimizing them.
And I think with that we can thank the speaker again and go towards rounding off today, but not before I make 2 announcements. The first one is now I need to maybe stop the recording.